The cosmos holds many different kinds of stars. There are huge, giant stars, hundreds of times larger than our sun, that burn bright and fast. For the most part, alive for only a few 100 million years. There are stars like our sun, relatively smallish stars peppered throughout the galaxy. They shine at a more moderate temperature compared to the giants and last for around 10 billion years. Our sun has been around about half that long and will die some 5 billion years from now. But the vast majority, around 85% of all stars in the sky, are cooler, dimmer ones, and they are known as red dwarfs. As their name implies, a red dwarf is small, no bigger than half the size of the sun. They are also very dim. The brightest known red dwarf has only 10% of the luminosity of the sun, and they generate as little as 1/10,000th of the energy. The smallest among them are barely able to shine at all. These smaller red dwarf stars, those that are a mere 7.5% the size of the sun, are the smallest objects in the universe able to shine by the process of nuclear fusion. But their small size and dim luminosity has one big advantage. Red dwarf stars live the longest. Relative to all other stars in the sky, they are immortal. Their lifetimes extend into the trillions of years. They will live roughly 1,000 times longer than the sun, and 100,000 times longer than most giants. Red dwarfs live so long because they burn their hydrogen fuel slower than brighter stars. They are of such small size and generate so little energy, they can fuse their hydrogen more efficiently. To understand why, we need to look at what's underneath the surface of a star. All stars, regardless of their size, have layers underneath. The details of what and how many layers depends on its mass. The sun, for example, has a layer known as the radiative zone. It lies between the core and another region called the convective zone. When a photon of energy is generated in the sun's core, once it hits the radiative zone, it hits a kind of wall. Energy can only pass through this zone by collision with another atom and re-emission. Giant stars have a much smaller radiative zone and a larger convection zone. Radiation by fusion is a more efficient process here. This process of collision and re-emission takes a lot of time. It can take a photon passing through the radiative zone nearly 3 million years just to get to the surface. These photons from the sun had to go through a lot, as well as millions of years, to reach our eyes. Red dwarf stars, on the other hand, do not have this radiative zone. Photons emitted from the core go straight to the convective zone, where the hydrogen gas is more efficiently mixed with the core, allowing more of it to be used. Red dwarf stars are able to convert virtually all of their hydrogen fuel to helium, to a degree other stars with large radiative zones cannot. So how will red dwarfs die? Long after all other stars have perished, red dwarfs will still be shining. Glowing dimly and feebly, these smoldering embers of creation will be the main source of radiation in our universe. Dim reminders of a once bright and vibrant universe. Long after all other stars are gone, after every ounce of their hydrogen has been spent, red dwarfs will slowly fade into oblivion, their embers cooling. And for the first time since the beginning of the universe, the sky will be dark.